In this video, we're going to discuss other ways of making carboxylic acid derivatives. And the first reaction we're going to look at is called the Baeyer-Villiger oxidation. Um, so it oxidizes ketones to esters, and it can oxidize aldehydes to carboxylic acids. So the reaction here, and I'll show you some generic reactions, is simply reacting an aldehyde or a ketone with the reagent of a peroxy acid. So we could use peroxyacetic acid, we could use MCPBA as a typical peroxy acid, which we've already seen this reagent being used to oxidize alkenes. So that's one thing that we have to worry about if our compound has an alkene functional group and a ketone or an aldehyde. The peroxy acid will actually react with both of them. But in terms of the generic reaction, we see a ketone reacting with a peroxy acid to give us an ester, and we can also react a generic aldehyde with a peroxy acid to give us a carboxylic acid, right? So these are new ways of making carboxylic acid derivatives. So we see that we can make an ester through the Baeyer-Villiger oxidation of a ketone, and we can make a carboxylic acid through the Baeyer-Villiger oxidation of an aldehyde. And this is simply, with the aldehyde, simply a new way of oxidizing the aldehyde to a carboxylic acid. We know other ways of doing so, namely the chromic acid as a reagent, right? So now we have a new reagent to oxidize an aldehyde to a carboxylic acid. The big new thing here is oxidizing a ketone to an ester, right, to make an ester carboxylic acid derivative. And if we take a look at the mechanism of this reaction and how it plays out, I'll show a ketone, since this is kind of the new reactant here, reacting with an acid, and we should know by now that the first step is going to be proton transfer. We've seen that carbonyls react with acids and they undergo proton transfer at the carbonyl oxygen. So the resulting species is this protonated carbonyl, which increases the electrophilicity of that carbonyl carbon, and we get the conjugate base of the peroxy acetic acid, or peroxy acid. So this is the peroxy acetate. And that peroxy acetate, just like a normal acetate, is nucleophilic, so it's going to undergo nucleophilic addition to the carbonyl carbon. And the result is this, right? So we have R, we have our tetrahedral carbon, the OH, and then the other R group. And now we have our nucleophile attached, that is this peroxy acetate. Now something interesting happens at this stage, and what we see is the reformation of the carbonyl, and now one of the R groups is going to migrate the bond between carbon and one of the R groups is going to actually migrate to the oxygen that's attached to that carbon. And so once that occurs, then we get bond breakage between that oxygen-oxygen bond. So the key is that there is a migration step of one of the R groups, and we'll discuss which R group actually undergoes migration in just a little bit. But the key in terms of the mechanism is recognizing that one of the R groups moves and it kicks off an acetate. So the result looks like this. Now we've reformed the carbonyl, right? That's still protonated. So that carbon still has the oxygen attached. The R group has migrated to the oxygen, so now we've created that OR bond of the ester. And of course we create the carboxylate that comes off of it. So after that we simply have to deprotonate the carbonyl oxygen, and the result is an ester, and then of course the carboxylic acid that comes from the peroxy acid to begin with, right? So we form an ester, and then as a side product we form a carboxylic acid. All right, So let's think about what happens when the two R groups are different. Well, when they're different, there's an order of selectivity of the group that migrates, right? And that order of selectivity is kind of, I would say, maybe a little inconsistent. So when we look at the R groups attached, the first one that actually migrates is going to be a hydrogen. So if there's a hydrogen attached to that carbonyl, it's going to be the first to migrate. This is why aldehydes form carboxylic acids. The hydrogen of the aldehyde migrates to the oxygen that that is attached when the peroxyacetate or peroxycarboxylate attaches to form that tetrahedral intermediate. And so if you have a hydrogen on a carbonyl, if you have an aldehyde, it's going to be the first one to migrate. That's followed by tertiary alkyl groups. So if one of the two R groups is a tertiary alkyl group, it's going to be the next to migrate, followed by a secondary alkyl group, which is actually followed by an aryl group. So an aryl group, right, benzene, its order of selectivity in this migration is actually after a secondary alkyl group. And then you have primary alkyl groups and then a methyl group. So the methyl group would be the last one to migrate. And if you have a methyl ketone, that methyl group is it's never going to migrate, right? Okay, so let's take a look at a couple of examples. Here I'm using trifluoro peroxyacetic acid reacting with a ketone. Here the ketone, if you look at the groups attached to the ketone, I have a methyl group and I have a secondary alkyl group. So we know that that secondary alkyl group is the group that's going to undergo migration, and so in essence we have insertion of the oxygen to form our ester in between the carbonyl and the secondary alkyl group on the left. So the result looks like this, right? I have my secondary alkyl group, oxygen attached to the carbonyl, attached to the methyl group, and I form an ester in that process. And I can show you another example here. I have another ketone. I'm reacting with MCPBA. So remember, metachloroperbenzoic acid is going to be our peroxy acid. And if I look at the two groups attached to the carbonyl, I have an aryl group, and then I have a primary alkyl group. So the aryl group takes precedence, is selected over the primary alkyl group, and therefore it's the one that's going to migrate. And so we have the oxygen insertion in between the aryl group and the carbonyl. So we get this as our product. Now the other kind of cool thing about the Baeyer-Villiger oxidation is that if I take cyclic ketones and treat it with a peroxy acid like MCPBA, I get insertion. Now, of course, this is a symmetrical cyclic ketone, and so there is no real precedence of one over the other side, obviously. But the cool thing is I get an expansion of the ring, and I form an ester, a cyclic ester, and so we know that that is a lactone. Now, another reaction that we're going to look at to make carboxylic acid derivatives is called the Beckmann rearrangement. And the Beckmann rearrangement takes initially a ketone and it treats it with an amine type derivative, right? So NH2OH. And so when NH2OH reacts with a ketone, remember amines react with ketones to form imines. And so when this particular amine reacts with a ketone, it forms what's called an oxime. So you have this imine, carbon-nitrogen double bond, and attached to the nitrogen is that OH group. So that's where we get that oxime name from. Now when oximes get deprotonated, so under acidic conditions, and usually this is fairly acidic conditions, what happens is another type of migration we're going to see, but you can form amides this way. So you have another alkyl migration to form an amide. And if we take a look at the mechanism of this reaction, we'll see some similarities between it and the Baeyer-Villiger oxidation. So the first step is, the first step obviously is the ketone forming the oxime. And I'm not going to show that because we've already talked about that particular mechanism. But when the oxime is in acidic conditions, we get protonation, right? So proton transfer. And in that process, we form a good leaving group from the water. Now, when water leaves, at this step, one of the R groups migrates to the nitrogen. Right? So here is our migration step. So one of the R groups migrates to nitrogen and the water leaves. The result looks like this. So now I formed a carbocation. One of the R groups has shifted to form a nitrogen alkyl bond. The other R group is still on that carbon. And of course, I can draw a resonance stabilized structure by donating a pair of electrons from the nitrogen into that alkenyl carbocation, and I form this nitrile cation type species. Now, of course, in aqueous conditions, what we have is we have attack of the water, right? Attack of the carbon by water, our nucleophile, and that carbon-nitrogen triple bond breaks. And so we form this species here. And you see that the water has to now be deprotonated. And of course, we can use another water molecule to deprotonate that. And the result is this structure here. So now we have a neutral species, but we regenerate our acid, and now that acid's going to be it's going to protonate the nitrogen because it's fairly basic. And when that nitrogen gets protonated, now we have this species here. So I'm going to draw that again on the next page here, and see if we can think about what's going to happen here. So now the nitrogen is protonated. The carbon attached to it has this OH group. I can actually draw a resonance structure where I donate a pair of electrons from the oxygen to the carbon to create a carbonyl, a protonated carbonyl. And now the bond breaks between that carbon-nitrogen to create now just a sigma bond between carbon and nitrogen and a lone pair of electrons on the nitrogen. And of course now you could see that if I simply deprotonate that carbonyl, I get an amide, right? So this is how we go from an oxime to an amide. And it's a kind of a cool little reaction, right? I take a ketone, I react it with NH2OH in some type of acidic conditions, and I get this nitrogen insertion, very similar to the Baeyer-Villiger oxidation, where it's inserting an oxygen. Here I have an insertion of a nitrogen at one of the R groups. The selectivity is not quite the same. It's actually kind of unpredictable in terms of its selectivity. And so generally speaking, we're going to use symmetrical ketones in this type of reaction. So I can show a cyclic ketone, right, with NH2OH, and I get a lactam in the process. Okay, so two insertion or migration reactions to form esters and amides, and you kind of see there's a parallel between them. Now, another reaction that we're going to take a look at, actually there are two reactions, is how do we make nitriles? And of course, we know one way of making nitriles by nucleophilic substitution reactions of alkyl halides, which is what we talked about in the very first semester. But a new reaction is a dehydration of amides, right? So the first reaction, the substitution reaction, where you take an alkyl halide, you react it with sodium cyanide or potassium cyanide or lithium cyanide, doesn't matter what the metal ion is, and you get this substitution reaction and you form nitriles. That's probably the easiest way of forming nitriles. So a generic reaction is where I take, here I have a primary alkyl chloride, and I treat it with sodium cyanide, and I make my nitrile this way, right? The new method is taking a primary amide and treating it with P2O5, so diphosphorus pentoxide, and I add heat to this. And so when I do so, I get complete dehydration. I lose water. So if you take a look at that amide, the nitrogen has two hydrogens coming off, and then of course I have the oxygen on that carbon. So one way that you can remember this is if you have P2O5, you're going to lose water, right? And that water comes from the two hydrogens on the nitrogen and then the carbonyl oxygen. So here's an example. Again, primary amide reacting with P2O5, and the carbon, right, nitrogen creates a triple bond. I lose water, so I create this cyanide. The last reaction we're going to take a look at is how to make ketenes. So we've talked about ketenes, but we've never really talked about how to make them. And actually ketenes are relatively easy to make, but they're also relatively unstable. And you make them by eliminating HCl from an acid chloride. The way you do this is you use tertiary amines as bases. So remember, if I have an acid chloride, acid chlorides react with amines, but the amines have to be either primary amines or secondary amines because you have to have a hydrogen that can be deprotonated. If there are no hydrogens on the amine, then it won't react with the carbonyl. Instead, the amine will react with an alpha hydrogen, so a hydrogen attached to an alpha carbon. Alpha carbons are carbons attached to carbonyls. And so what happens is you get deprotonation. The pair of electrons go to form a carbon-carbon double bond, and in that process the carbon-oxygen bond breaks and the electrons go up to the oxygen. You form what's called an enolate type species, and then that enolate, so it's going to reform. We have a good leaving group of as a chloride, and so we're going to kick off eliminating the chloride, reforming the carbon-oxygen double bond. Now that carbon that is currently sp2 hybridized becomes sp hybridized, and so we form a ketene. In this particular example, we have an R group and a hydrogen, but we could have two R groups or we could have two hydrogens. It doesn't really matter. So, typical type of reaction, taking any type of acid chloride. Now notice the acid chloride has to have a hydrogen on the alpha carbon, has to have at least one hydrogen on an alpha carbon, otherwise you'll get no reaction. And I treat this with triethylamine. I could use triisobutylamine. I could use triterbutylamine. Any of these types of tertiary amines will work. And I get a ketene. And keep in mind, you know, ketenes, that carbon is sp hybridized, so we have this kind of linear structure, very similar to that of accumulated dienes and, of course, alkynes, right? So that is how we make carboxylic acid derivatives and acyl-like compounds. We see we can make esters and amides through migration process. We can make nitriles through substitution or dehydration, and we can make ketenes through the elimination of HCl from an acid chloride using a tertiary amine.